This program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest UCTV programs.
And it's my pleasure to introduce our next keynote speaker, Michael McQuade. Michael is the Vice President for Science and Technology at United Technology Corporation. He's responsible for strategic guidance of their research and development programs. Has a great interest also in manufacturing, obviously, and that will be something he'll be talking on today. Michael has previously worked also at 3M and at Kodak. He's a graduate, all 3 degrees from Carnegie Mellon. He's also, appropriately, a member of the Secretary's Advisory Board and is a member of the board of the Carnegie Mellon Institution. Michael is going to talk to us about materials for energy efficiency and manufacturing.
Thanks, Dave. Thank you. Morning, everybody. We were laughing before the break. I think I've reached the pinnacle of my career, so you can decide which one it is. Either the secretary was a great setup man for my talk, or he gave my talk. So we'll see which one it is here in a minute. So I'm going to try and do 3 things. I'm going to very quickly just give you a quick reminder of UTC, but to help you understand why we're here. I want to talk primarily about materials. I'll give you a couple of examples of why materials and material sets matter to us in the current products we have. And then I really want to spend a bit of time just helping frame what I would say are some of the issues and opportunities around the interaction between materials and processes, particularly as it relates to energy efficiency of the manufacturing process and of the materials themselves. So let's take a quick look. So this is UTC. For those of you who don't know us, most people either know us as an aerospace company or they know us as a commercial company. So on the aerospace side, we make jet engines, helicopters, and essentially everything else that goes in a plane except for avionics. So we make all the actuation, we make all the air management systems, the electrical generation, distribution, cabin pressure, et cetera, all those kinds of things. On the commercial side, we are, if not the largest, one of the largest suppliers of stuff that goes in buildings. So HVAC systems, security systems, energy management systems, elevators, and a sort of a long, great business for us in doing those kinds of things. So we're about half and half between the 2 sides of the business. And the theme here is we're a company that makes stuff. So we actually cut metal, we bend parts, we actually make things. And so we're technologically denominated. But at the same time, we're also a company that by and large has to deliver more energy efficient solutions to the customers that we serve to help them do what they do with less energy along the way. So the last corporate overview slide, I usually go from left to right on this slide. I'm actually going to go from right to left. This is the sustainability roadmap we have for the company. Start on the right-hand side. Advocacy really means being part of the voice for specifically energy efficiency. And how do we help advocate for energy efficiency as not only low-hanging fruit, but financially viable opportunities to invest in the energy security, energy cost reduction in the United States. So we have a number of places we do that. Places like here, sponsorship for the Institute, some of the seminal work done at the World Business Council for Sustainable Development on energy efficiency in building opportunities. My colleague Bill Sisson is here, who helped lead that project and is leading the 2nd generation of that. You're going to hear from Kateri Callahan tomorrow from the Alliance to Save Energy on a program that we were part of to help look at recommendations for doubling energy productivity in the country between now and 2030. The point of the advocacy on the right-hand side of the slide is we believe you can't advocate for something unless you have a ground to stand on. And so now you go to the left-hand side. The first question is, what have we as a company done as part of our internal strategy and execution to be more energy efficient? And so starting in, if you look at the graph on the bottom left-hand side, the punchline is from 97 to 2012, the size of the company went from about $20 billion to close to $60 billion. And the energy consumption in the company went down 19%. So we almost tripled the size of the company. Energy consumption in real terms, not energy per unit dollar, in real terms went down. Through all of the kinds of blocking and tackling that everybody should be doing. It's cogeneration facilities, it's new lighting systems, it's new buildings built to LEED standards, et cetera. So you start with, can I say that I am using all the things I tell other people to do effectively in my company? And then in the center is why we exist. We exist to bring energy efficient solutions to the customers we serve. So I'll talk a little bit about the Otis Gen 2 elevator systems here in just a minute. Jet engines, the Pratt & Whitney Pure Power engine that Secretary showed on a picture there before, where it's rather than a couple of % increase in fuel efficiency as all jet turbine engines have done generation to generation since the 1950s. This is about an 18% improvement in efficiency through a combination of unique architecture and material sets used in that engine. So those are the kind of things that we help to deliver to our customers. And then finally, the quote at the top is from the former CEO, George David, who basically said, why do we exist? We exist to combat gravity and weather. We make things go up when they want to go down, and we make things hot when they want to be cold and cold when they want to be hot. And that's sort of who we are. The second quote doesn't have an attribution because it's me. This is one I use a lot of times when I give talks. Basically, to help people understand, we tend not to outcompete people because we market better or because we price better. We have to be price competitive and we have to be operationally competitive. But at the end of the day, people buy stuff from us because it technically outperforms the other options that they have. And more, that means how does it perform in its energy usage or in reducing the energy consumption of the customers that we serve. So let me give you a couple of examples now to bring this back to materials. So this is Otis, right? So we started the first safety elevator in the 1850s. And what drives elevators? It's a box on a string. It's a complicated box on a string. And the competitive vectors now are making it a less expensive box on a string, but also looking at how the elevator performs from a safety point of view and from an energy usage point of view. So it took us a long time, from 1850 to roughly 2000 to come up with Gen 2. So it's a pretty slow-moving industry. Gen 2 was a major breakthrough in elevator systems. So the challenge is that elevators with steel ropes, as the elevator shaftway gets higher and higher, the ropes get longer and longer, they need to be thicker, and the turning radius across the sheave, that orange object you see, gets to be very, very large. That means the motor drives have to get very large. That means you're lifting a lot more weight on the ropes. That means the space taken up in the building by those motor drives has to be much larger. You don't have usable space. So what we did effectively is a material science problem. We took the large steel cable, took it apart, and embedded it as a bunch of smaller steel cables inside a polyurethane coated belt. That belt has a much, much smaller turning radius. It eliminates lubricants because now I have a coated polyurethane surface over a sheave. We also are able to do things in a system like that where we actually resistively measure the load on those individual fibers to determine the lifetime of the belts along the way. And essentially went from steel rope elevators to coated steel belt elevators with about a 70% reduction in machine volume. That's the picture on the bottom that you see. That's a standard rope, sheave, and motor drive system, and then that's a coated steel belt system on the left-hand side. 75% reduction in the size of the machines and reduced power consumption of those machines by 50%. Now, there's some really big, important numbers associated with power consumption in elevators, and we've reduced them dramatically through a whole series of material challenges. Coated steel belts, advanced magnetics for motor drives, either rare earth materials or non-rare earth materials. We're changing all of the power electronics into silicon carbide, looking at gallium nitride on those elevator systems. And most importantly, the Gen 2 elevator systems are regenerative. So they recapture the energy when the elevator is unloaded in the negative direction. We put that back either into a battery that's used to drive the elevator, or we put it back into the building. It saves about 75% of the energy in the building, point number one. Point number two, in parts of the world where power is not continuously available, rural markets, those battery-driven systems allow you the safety to be able to run those elevators when the power goes out in the building. So big opportunity for us going forward. We also look at something we call topology optimization. I put this slide because I'm going to come back to this in just a second. This is the ability to essentially take a volume space, use advanced Monte Carlo methods to say, what is the minimum material set I need to serve the function of that volume space? And in this case, the function is the cab of an elevator. And I can decide what's the minimum number of parts. I can constrain it by manufacturing process, energy embedded in the manufacturing process, or I can constrain it by material weights and material sizes. So looking at being able to explore the entire design space without starting from a preconceived notion of how the part should be built along the way. I'll come back to that because it's important in some material stuff I'll talk about in a moment. Okay, so then this is just for fun. This is why we worry about all these things. If you're in the elevator business, you make no money on these big projects, but you have to do them because they're the signature projects of all time, right? So these are the largest buildings in the world. Just to give you perspective on what drives the elevator business, these are the 10 largest buildings either in the world or soon to be. The total number of elevators sold in China next year is close to 500,000. So while you pay attention to this, when you're designing for cost and manufacturing and factory locations and all those kind of things, you worry about the size of a market that's rapidly urbanizing. The tower second from the left is the Burj Khalifa tower. So we have the elevators in that building. It's an 800-meter tower. The tower just to the left of that on the far left-hand side is the Kingdom Tower, being in final design stages in Saudi Arabia. That'll be the first building to be over a kilometer tall. And so getting the elevators right for that is crucial. I want to talk briefly about membranes. If I advance here, let me just go through here. So this is energy consumption in the world. So standard picture we've seen, buildings about 40%, industrial about 30%, and transportation about 30%, with some comments on where membranes impact energy use or energy efficiency or performance. And I just want to highlight one for you just for a moment, just to sort of, again, this is in the category of how do materials matter for us as we go forward, right? So this is the fuel system unit or fuel stabilization unit. You may not know this, but in many jet engines, in particular military fighter engines, you actually use the fuel as a coolant. So you pipe the fuel around through the engine and use it as a heat exchange fluid. The problem with that is as the fuel gets hotter and hotter, its ability to extract or keep the oxygen in the fuel gets better, right? The oxygen stays in the fuel at high temperature, and that induces coking when the fuel is actually burned in the combustor of the engine. So the question is, how do we deoxygenate fuels so that we can use them as a coolant in the aircraft? There's a membrane issue here that we have here. So we've designed these membrane systems where you actually, in very high pressure, drive the fuel through a polymer exchange membrane. The challenge here is that conventional polymer units that we use here are very, very prone to pinhole defects in the manufacturing processes. These fuel systems tend to operate at roughly 100 psi. Having leaks in these fuel systems is a bit of a problem when you're moving sort of 600 or 700 degree fuel around a hot engine. You tend not to want leaks around there. So there's a material problem here. How do we get polymer membranes, diffuse polymer membranes that have much, much more uniform coating, sort of factor of 10x better coating and pinhole capability, lower weight, what's the optimum geometry for these processes along the way? And so these are the kind of things that we look at when we look at how materials impact our current sets of projects. I want to drop forward to, I skipped some stuff here. So let me talk about manufacturing, because this is really what I want to sort of stimulate the discussion about. Everybody in this room knows we have, and the Secretary talked about this sort of significant investment that we're making in manufacturing technology and advanced manufacturing in the company. And I want to get sort of the focus of that, not just on manufacturing, but on the interface between manufacturing and material sets and material technology as we go. So this is something we call ATOM, which is Advanced Topology Optimized Manufacturing, or Additive Topology Optimized Manufacturing. It's the combination of topology optimization, being able to define the minimum volume space requirement of the product to do its function, at the same time being able to create those products in an additive fashion. So I'm no longer starting with the constraint of having to remove materials, particularly hidden cavity materials. And so a bunch of technologies like additive manufacturing for direct metal laser sintering, or technologies like cold spray applications that we have. All of those are part of the portfolio now, and they represent, I think, for all of us involved in these kind of businesses or in this technology base, a significant opportunity for us to define a new process for bringing material sets and manufacturing process to market. That includes very substantial, what we call ICME, Integrated Computational Materials Engineering, where the modeling and simulation of the materials themselves and the modeling and simulation of how the materials work in the processes that we're putting together are a big part of what we're trying to do here. So an example of that, this is some work that we've done on what we call physics-based modeling. So we cut a lot of stuff, right? We make things out of metals, and we have hundreds and hundreds and literally probably thousands of 5- and 6-axis machines around the world that are cutting metal. It's a very costly thing to do. The machines are expensive. You're constantly looking to optimize volume. It turns out that until recently, we did what most people do. I take a piece, I decide how the piece is going to be cut heuristically. Heuristically really means Bob over in the corner, who's been doing it for 25 years, knows just how that piece should be cut. And historically, what we do is we look at the part that we're going to put on the machine, and we determine what's the fastest, slow speed we have to cut that machine, cut that part. What's the most complex portion of the part, and I set the machine up and the tool drive and the speeds to operate at that speed, and that sets the overall throughput on the machine. So we launched a program a couple of years ago in the research center, basically where we now model what happens at the physics level at the tool cutting surface. Burnishing, annealing, skiving, cutting, spalling, material interaction, chemical interactions. We now do full physics-based modeling on what actually happens on the tool. And with sufficient computational resources, we can actually do that for the entire geometry of the cut part. And what comes out of that then tells us what's the fastest speed we can actually drive the machine at every spot in the cutting of the piece that we're working on. And it turns out that most of our machines have variable cutting speed capability in. So offline, you process the part, you do all the physics for both the tool and for the piece itself, and you determine what's the new tool path and tool cutting speed that we use. And these are just some examples. So IBRs, sort of integrally bladed rotors in our turbine engines, reductions in speed for the bottom one on the right-hand side. So this is an impeller in one of the air cycle machines on the 787 that we do for Boeing. 40% reduction in time for the part in the machine. So when you're constantly, so there's an energy savings associated with it, there's a time savings associated with it, and obviously there's a capital savings associated too as you go forward. So you can see the interaction between how we model materials, how we develop materials, and how we develop our new manufacturing methodologies. Just a couple of additive manufacturing technologies that we have in play right now. Most people are familiar with these. I bring these up because the real challenge for all of us is how do we marry this to the materials themselves? It's one thing to say, I know how to take certain kinds of steel and put them into powders and make them on additive manufacturing, but how do I substitute across the entire range of aerospace materials or other industry materials? And what's the energy budget that's associated with preparing those materials in a different way? So additive manufacturing becomes both an opportunity for us for prototype parts, it becomes an opportunity for low volume specialty parts, and it becomes an energy savings opportunity for us. So just to give you kind of a feel for this, this is sort of the general process. On the top is a conventional method. I take an ingot, I cut a lot of stuff, I make the material, I cut a lot of parts out of it, I basically remove all the stuff I don't want, and I end up with a finished product. And roughly sort of first order estimates can tell you that there's somewhere in the range of 30 to 40 kilowatt hours per kilogram of material manufactured. On the bottom, with an additive manufacturing part, once I have the powder, I am only using energy for material that is used in the part. So I'm only using energy for a 10th, a 20th, or a 30th of material, and that's the energy that's embedded. Now, the life cycle analysis says where'd the powder come from in the first place? Back to the chart that the secretary showed, is it actually cheaper to have powdered titanium partway through the process and not have to go through the additional step of putting it into billets and ingots along the way? Are the powders more special in a way that requires more energy? So there's a significant piece of work that we all as an industry and academia need to be doing on looking at how we look at total life cycle budget for these kinds of things. We can think about additive manufacturing for small volume parts. We can think about additive manufacturing for large volume parts from an energy efficiency point of view. And I think that's an important issue for us as we go forward. And then just to look at, when we look at direct metal laser sintering, this is sort of a chart that we're running on what are the material issues associated with taking that process and using it as a replicant for the processes that we do today. Right? Two ways to look at this. One is with these new technologies, new manufacturing technologies, we can do things we didn't do before. You take a complex part, a fuel manifold for us may have multiple internal channels in a block of metal. And if you do that with a conventional casting process or molding process or casting process, all of those channels have to be visible and accessible from the outside because you have to do secondary machining. If you're building a part up layer by layer in a 3D process, you have the ability to fundamentally change the internal part of that part in a way that allows you to have hidden cavities and hidden crevices. The other issue that we need to be working on, the comment about sensors and acquisition of data, analysis of data, is how do we marry real-time in situ quality control to parts that we're making in additive manufacturing processes. We need to be designing processes so that I don't create the part on one machine, take the machine off, and measure, analyze, and qualify the part on another machine. So how do we do that with sensors, with multiple light sources, with multiple sensing systems that are directly part of the manufacturing process so that we can get overall flow put together? So finally, and then we'll open it up for some questions or comments. So in general, I would say we're moving beyond what I would call product architecture. So that is, how does the part do what it does, to how do the materials and processes come together to enable the part to do what it does more efficiently, right? And I would argue that this transition to material science and manufacturing science is yet another opportunity for this country in particular, to do what it has done multiple times in the last 100 years. We talk about the competitiveness of this country. The competitiveness of this country is one of the fundamental levers that we stand on has been the still unique to the world triumvirate of academia, industrial research, and government-sponsored research. It led to the physics revolution in mid-century. It led to the computer and microelectronics revolution in the second part of the last century. It is driving the bioscience revolution in the country. It needs to drive the materials and manufacturing science. And all parties need to be at the table to make that happen. So thank you very much, and let me open it up for questions.
Thank you, Michael. If you have a question, please come up to the mic. While we're waiting, I have a question for you, Michael, that was inspired by your comments here, especially about advanced manufacturing and the opportunities. As we know, President Obama has announced a major initiative to inject some new support, especially for research into developing advanced manufacturing. Could you comment and elaborate on what you see as the opportunities, especially for those of us assembled here? We have people from not only academia, but from industry and from government. If you could just give a few pointers to them, that would be interesting to hear.
Sure. So first of all, I think it's a very, very important thing we've done. I would start by saying I think we need to keep very clear sight of the fact, not turning it necessarily to the investment in manufacturing, advanced manufacturing in this country is a significant economic driver. Whether it's a significant economic driver in recreating the numbers of jobs we used to have in manufacturing, I think is an open debate. But it is a significant creator of economic value by having our manufacturing technology and our innovative technology, our innovation ecosystem be in the same place. That will lead to the kind of high-skilled manufacturing jobs that will help drive the economy. So what do we need to be doing? I think there's sort of the reductionist view. It's material science technology, it's manufacturing technologies, it's new manufacturing technologies. But I think more and more we need to be approaching the investment in the research from a system level point of view. And I think from a university point of view, from an academia and national lab point of view, I think making sure that we are putting the research in this area of manufacturing directly connected to the material science and material engineering community is where we're going to get success. So I think those two things have to come together as we begin to figure out how we're going to invest in advanced manufacturing in the country.
Thank you. Other questions?
Uh-oh.
Okay, Michael covered it all. Thank you very much for a very stimulating talk. Oh, here we have one. Stephen Chu.
It's actually not a question, but it's more of a comment, and it goes to in the final assembly OEM manufacturing, it is very debatable whether there would be jobs. But if you look at the whole ecosystem, including the supply chain, there is no question, going back to the wealth creation in the United States, that part of it, there's a no-brainer, because it's the supply chain. And then all the secondary jobs and the service jobs and everything else go with it. And so, without a doubt, whereas some purists would say, well, a high-tech manufacturing won't actually add that many jobs. If you look at all the underlying structure beneath that, there are many, many jobs.
I agree. In some sense, we're saying exactly the same thing. To me, that's the economic creation that we have along the way. So my only comment here is that we do need to look as broadly as possible at what the economic growth that comes from manufacturing is.
Yep. Question here?
I was curious, interested in your company's view of the industrial internet and what that means to you in terms of information technology and exchange.
Well, I think it means a lot. People use industrial internet to mean a lot of things. Industrial internet to us means simply that the things that we do become more intelligent. So how do we manage fleets? Right now we have roughly 2 million elevators that we service around the world. How do we make sure that we have real-time access to those? From a research point of view, that's significant research in sensors and communication technology. It is also very significant research in prognosis and health management, so large-scale data reduction. How do we look at doing health management projections on rotating machinery? How do we do those so that you can actually life dynamic parts in aircraft in real time as opposed to lifing from fundamental design principles in the beginning? So it's a very big opportunity for us. It cuts across all the product families that we have. I would also say there's a very, very significant issue associated with cybersecurity of those kinds of systems. And so getting that right as part of the research theme and as part of the instantiation theme becomes important.